a straight wire, or yeah, with a charge per unit length on it like that. So charge per unit length is lambda, as before. You want the electric field at a distance r from it. Okay. Construct a cylinder of radius r. Construct a cylindrical surface of radius r with its axis being on the wire. Now, take an element of area here. The area vector is dA. Now, this is a very long, essentially infinitely long wire. Therefore, due to symmetry, if there is any electric field at that point, it should be either going away, radially going away, or going towards the wire. And we know that it would be going away if the wire had positive charge, and it would be towards the wire if it had negative charge. Okay, now let's look at the integral of E dotted to dA, which is equal to Q equals over epsilon naught. Now, excuse me. Look at E and dA. They are in the same direction. So as before, this is just E times dA. The cosine of the angle between them is 1. So you get the integral of magnitude of A times magnitude of dA equal to the charge enclosed. How much charge is enclosed? Well, the length of this cylinder, let's call the height of this cylinder h. And charge per unit length is lambda. So the charge that is inside the cylinder is lambda times h. That's how much charge you have inside the cylinder, divided by epsilon naught. Okay, again, E comes out because because of symmetry, it has to be the same everywhere on the surface. And by the way, that integral should only be evaluated on the side wall of the cylinder, not on the upper face and lower face. Why? Because if any area that you took there, the vector dA is going up or down here, the bottom is going down, whereas electric field is radial, which means that they are perpendicular. So E dotted to dA on the upper face and lower face going to be 0. Therefore, the only contribution to the integral would be from the side wall. So that would be E times what? Times the area of the side wall of the cylinder. What is that area? Think about this. Suppose that you have a piece of paper like that. And then make it circular, make it look like this. Okay, and let's say you tape it here. Okay, it's a circular, make it circular, so it's a long rectangular piece of paper and then we bring the two ends together and make it circular, look like a cylinder like this. But it's open at the top and the bottom. So what is the surface area of this? Now the side wall of that cylinder is just equal to length times width here, right? Length of a paper times width. But the length of a paper in here becomes 2 pi r, which is the circumference of this circle. And then the height here, and then this edge here is your width, which means that the area is going to be 2 pi r times h. And that's equal to lambda h divided by epsilon naught. H cancels out, and from there you get E equal to, well, we used capital R there, the capital R. So we get E equal to lambda over 2 pi epsilon naught R, which is the same result that we had before. But here we only got it in what, like 3 or 4 lines of calculation. So you see that because of the symmetry involved in the charge distribution, Gauss's law very quickly gives us the result. But the symmetry here is that this is a long straight wire with a uniform charge distribution. If the wire was not long, if it had a finite length or short length, and if it was not straight, but if the charge distribution was not uniform, then Gauss's law would not be able to give you the result. Okay. Another example of extreme importance is when you have a very large sheet of charge. Let's say you have a very large or wide sheet of charge with a uniform charge distribution on it. Okay, think about a very large sheet of large with a uniform charge distribution on it, and let's say there is a charge of sigma coulomb per unit area. Okay, we have sigma coulomb per unit area charge on this sheet. So we want to know what the electric field is at some point, some distance, let's say distance d